Hello, everybody. This is the lecture on minerals. It'll be in parts. I have no doubt about that because this is a longer presentation, about 80 slides or so. So it'll be broken up into parts. But this is where we really start to introduce kind of the fundamental building blocks of rocks. Rocks are ubiquitous and are made of minerals. And understanding what a rock type is greatly depends on the minerals that it contains. And one thing about minerals, as I'll discuss, is that they're chemically distinctive. They're sort of the base unit, if that makes sense, of how rocks are constructed and what their compositions are. And minerals have some very distinctive properties that make them sort of unique and distinct, and they're again, like I say, sort of the foundation of all the earth materials that we have on the planet. And so we're going to touch a number of areas here, some geochemistry, and if you haven't taken a chemistry class before, I'm going to do a kind of quick brush up on the components of atoms and how atoms bond and things like this with charges and things like that. Once we get through that, then we'll talk about minerals specifically. But I don't want you to worry. If you haven't taken any chemistry, I'll try to make this as simple as possible. If you have taken some chemistry, then this will be kind of a breeze for you for this first bit, and then we'll jump right into minerals. So as I alluded to, minerals are the building blocks of rocks, and minerals are, as I'll get into, chemically distinct. So, the atomic structure of a quartz is very different than the atomic structure of an olivine, and the atomic structure of quartz likes to be at low temperatures and low pressures, whereas olivine likes to be or is stable at high temperatures and high pressures. And as such, minerals tell us something about the area of the earth in which they formed, and they are the result or the product of magmatic activity that and the slowing and the cooling of magma at different temperatures and pressures, and that gives us this wide array of different minerals. There's thousands of them, I think, probably 5,000 or 6,000 distinct minerals. And as geologists, we use minerals as sort of the building blocks for rock types, but it's not just enough to know what a rock is based on its minerals. What's really important about minerals and rocks is that they tell you a story about the temperatures and pressures and other conditions that rocks form at. And that tells us a story about the dynamics of the earth. So I said to somebody last week, I think, that rocks are words, or maybe let's say minerals are the words in a sentence. The sentence are rocks, but the story is geology. So geology tells the story of the earth, and it uses words and sentences, i.e. minerals and rocks, to tell that story. But this is about the only time in this class that we're going to actually look at rocks and you're going to identify them and study them, because even though we're moving very fast and we're going to start to get into glaciers and topography and water and groundwater and flooding and all that sort of stuff, this is really the portion of the class where we actually do a deep dive into earth materials and with minerals and rocks. So here we go. So here we're going to do a little bit of sort of a brush up on chemistry, or maybe even introduction to chemistry for some of you. And I want to talk about elements, atoms, and atomic structure, because this is very important, because minerals are basically a combination of elements. They have a specific, each mineral has a specific atomic structure, and that atomic structure repeats. And knowing something about the atomic structure of a mineral also helps you to identify that mineral or understand characteristics of that mineral at the macro scale, at the scale that where you can hold something in your hand. Actually, technically, I should say, macro scale is like if you were looking at a whole universe or the whole Earth or the whole galaxy or the whole solar system. In geology, what we say when we're holding a hand sample, anything that's at the level of humans, we actually call that the mesoscale. So minerals in the mesoscale mimic their elemental and atomic constituents or elemental and atomic structures. And so it's really important that we define some of these terms. So first I'll talk about an element. So what's an element? So an element is a pure substance that cannot be decomposed into other pure substances by normal chemical methods. So an element is hydrogen. An element is helium. An element is aluminum, iron, silica, carbon. So the very basic building blocks of all matter in the universe are elements. And atoms are the smallest particle of that element, which can't be broken down anymore. So it's a group of neutrons, a group of protons, and a group of electrons all kind of hanging out in this like singular, unique and undivisible unit. And atoms can bond together based on basically their electrons for the most part. They can combine together to form compounds, and the proteins in your body are a compound. Aspirin is a compound. And this is where atoms of different types, say a carbon, a phosphorus, a bunch of hydrogens, can come together and bond in a certain combination and make up a compound. So here's the simplified view of an atom. This probably looks familiar to many of you. You might have learned about this in grade school or in high school, or maybe even some chemistry classes that you took here at the college. And this is a somewhat outdated model, but it illustrates the parts of an atom just fine. And it's loosely based on the way planets move around the sun in our solar system, let's say, where the sun is the nucleus here, and then the planets would be the electrons. And based on their charge, electrons appear in different rings around that nucleus. And for our purposes in this analogy with the nucleus, we would consider that sort of like the sun, and then the electrons sort of revolve around it like the planets do. Now, this is not how an atom actually works, and I'll get to that, but I want you to notice that the nucleus is a mass of protons and neutrons, and protons have a positive charge, and neutrons have no charge. And revolving around that nucleus, although in actuality the electrons actually just kind of appear or have probabilities of appearing around a nucleus, they have a negative charge. And they're very fast. Electrons are weird. And they tend to appear and disappear and move around through space and be linked up with other electrons in very strange ways. But electrons are the outermost portion of the atom, and those are the components that bond with other atoms based on basically electromagnetism and the charges involved. So atoms are very much like little magnets, and some have positive charges, some have negative charges based on the number of electrons versus the number of protons. That gives atoms a charge, and a +2 atom, let's say, and a -2 atom want to bond together to kind of complete those charges and sort of get to a net zero if you want to think about it like that. And that's how bonding occurs, and that's how compounds are formed. And as you might imagine, atoms are very, very, very small. So the spaces that atoms occupy, as far as the nucleus and the furthest electron away from the nucleus, or the valence electron as they're called, occupy a region of space about 10 to the negative 15 meters. So that's 0.00000000000000001 meters. So super small. And yes, I used my fingers to count that, and that was exact. So you're welcome. And like I said, we have older models of atoms and we have newer models of atoms. And on the left here, you'll see the kind of older model, the Bohr, Niels Bohr. He's a famous chemist and physicist. And he posited that there's the nucleus and has generally a positive charge, right? Because, well, actually it always has a positive charge because it's made up of protons, which are positive, and then neutrons, which are no charge at all. So it naturally exerts a positive charge. And then as such, it attracts negatively charged particles called electrons. And in the Bohr model here on the left, they sort of revolve around the nucleus. And there's different, what we call energy shells. So there's electrons that are very close to the nucleus, usually containing, or almost always containing, 2 electrons. And then each corresponding shell outside of that contains 8. And the outermost shell and heavier elements with, let's say 60 protons in the nucleus will have more shells, that is more subsequent shells moving out from the nucleus than something like hydrogen or helium, which just has 1 shell. Because the more positive a nucleus, the more negatively charged electrons it attracts. And so in the Bohr model, these shells are sort of like spheres or orbits where the electrons are orbiting around at greater distances, and the heavier the element, the more shells and the more electrons it has. But what's actually probably more accurate is the quantum model over here on the right, and it has the nucleus at the middle, just like in the Bohr model, but electrons aren't actually just revolving around like a planet. They're not just spinning like this. They're actually blinking in and out of space and appearing at certain distances around the nucleus. Similar to these shells here, where you have a shell closer to the nucleus, and then another shell a little bit further away, and then another shell even further away. Here you have electrons just having a probability of appearing closer to the nucleus here, and then a lesser probability of appearing out here, and then a lesser probability of appearing out here. And this is probably how atoms actually function and how those electron particles are actually interacting with the nucleus, where there's just a higher probability for certain atoms that they'll appear at the center, and then a higher probability that they'll appear here, and then lower probabilities that they'll appear out here. And we group elements based on their atomic weight or mass. And early on, and we still do, we group them based on their chemical properties. So we knew a lot more about how elements react with one another way before we had atomic microscopes and precision instrumentation where we could actually look at the nucleus and look at the units of atomic weight and atomic mass. And so here's some terms to get us started. The atomic weight is the number of protons and the number of neutrons in the nucleus. They are the heaviest parts of an atom. The electrons that that are bonded or bound electromagnetically to the nucleus have very little weight, if any. There is some weight or mass, I should say, to an electron, but it's minuscule compared to the sizes and weights of the protons and neutrons. And so we use those to illustrate the actual mass of an element. And the proton has an atomic weight of one atomic unit, and it has an electrical charge of +1. The neutron also has the same atomic weight of 1, but it has no charge. And the atomic number is the number of protons, and that is what makes an element that element. Okay? So carbon, for example, has an atomic weight. Oh, let's get my thing here. Has an atomic weight of 12. So what does that mean? Well, that means it has 6 protons, right? Each having an atomic weight of 1, and it has 6 neutrons with an atomic weight of 1. 6 plus 6 is 12. Carbon, in its stable form, has 12 protons and neutrons. So that makes up its weight. But what makes up its atomic number is just 6, right? So carbon 6, as far as protons, 6 protons, is what makes it a carbon. If you add or subtract a proton from the nucleus, well, now it's oxygen or nitrogen, right? So oxygen has a certain number of protons and nitrogen has a certain number of protons. But if something has 6 protons, it's a carbon. Now you can add or subtract neutrons from that and make that carbon heavier or lighter as far as atomic weight. But because the proton number doesn't change, it's still a carbon. And I'll get to this, but that's what we call an isotope, and that comes into play later on, especially when we're doing radiometric dating or geologic time, which we'll get to later in the semester. And again, we have electrons, and they are negatively charged particles that are attracted to the positively charged nucleus. And you can see that over here in this upper right figure here, where we have the nucleus in the center, and then the electrons appear in these shells that I talked about, where based on certain electromagnetic energies, the electron will be closer or farther away based on the size of the nucleus. So a larger nucleus will have more of these shells or more electrons in these shells, and then a smaller nucleus would only have, maybe 1 shell or 2 shells with different numbers of electrons in those shells based on the strength of that positive attraction. And for all atoms, there is an outermost shell that has some number of electrons. And these electrons are the furthest from the nucleus, and they can gain or lose electrons, and this creates ions. And we'll just take carbon again as an example. Carbon has a nucleus with 6 protons, and then it has electrons in its first shell and its second shell. And so in its stable form, carbon-12 with 6 protons and 6 neutrons, that nucleus has a +6, and so it pulls in 6 electrons to balance itself out. Once it does that, there's no more positive force being exerted by the nucleus, and so that electron is happy. However, shells want to get to a certain number. And without getting too in the weeds here, basically, the first shell, electron shell of an electron, can only take 2 electrons. That's standard across all elements. Then each subsequent shell after that wants to get to 8. 8 fills that shell out, and then depending on the size of the nucleus and the charge of the nucleus, it will build more shells. And this happens instantaneous. This is the creation of an element, right? So if you have carbon, which is +6, it fills its first shell with 2. Then its next shell, it fills with 4 electrons. And so it's happy having a complete first shell of 2 electrons, and then a half-filled second shell of 4 electrons. Remember, it wants to get to 8. So in this way, carbon has it's negatively, or it's neutrally charged because it has the number of electrons and the number of protons to make it happy, right? It has 6 protons and 6 electrons. So it's happy in this case, and in that it's electrically neutral because they balance each other out. But its shell wants 4 more to complete that second shell to get to 8. And so it will bond with other atoms that have 2 electrons in its shell that it's willing to give up, or 4 electrons, or 3 from one and 2 from another, or 1 from another, whatever, to get to that 8. And so this is how bonding occurs. And like I said, in order for atoms to bond together, they have to be in their ionic state. So let's talk about ions a little bit. Ions are atoms that have a positive or negative charge. And when they have a positive charge, that is more protons than electrons, so the electrons aren't balancing out the charge on the protons, there's leftover protons with no electrons attached to them. So they have a positive charge, we call those cations. And they lose electrons. So they donate electrons. And then we have anions, which are negatively charged, which means they have more electrons, and so they've gained electrons, right? And cations and anions bond to each other to form compounds. So I don't want to get too into the weeds here, but let's talk about bonding for a second. And bonding happens between cations, in this case sodium, and anions, in this case chlorine. And that forms sodium chloride, or table salt. Now, in their natural state, sodium is a soft silvery reactive metal, and chlorine is a poisonous gas. It's usually green in color. And sodium has 11 protons and 11 electrons, so it's happy, right? The charge is balanced there as far as that goes. And the chlorine has 17 protons and 17 electrons. So electromagnetically, it's also balanced. But the reason we call them cations and anions is because of the shells here, right? The outermost shell. Because we fill 2 electrons into the first shell, and then we fill 8 electrons into the second shell, this last shell, this third shell, which only has 1, because remember we have 11 electrons for sodium, this last shell only has 1 electron in it. Whereas with the chlorine, we have 17, so we have 2, plus 8 in the second, that's 10. And then in this outermost, we have 17. To get to 17, we have 7 electrons. So it wants 1 electron to fill that shell. This one wants to get rid of an electron to get rid of that shell and have, only 2 shells with 2 and 8, making it happy. And so it donates 1 of its electrons to the chlorine, and that electron sort of bounces back and forth, filling the chlorine's electron shell and getting rid of the outermost sodium electron shell, and so they're happy. It tricks the electrons, so to speak, into thinking that they have stable shells, and so they bond together and share that electron between the two of them. And so sodium and chlorine, in this case, bond together to form, like I said, ordinary table salt, NaCl. And that is a mineral in your mineral sets, halite, that cubic mineral that you looked at yesterday. And again, not to get too far into the weeds, but and you can go into your textbook to kind of read about this in more detail. But based on where these elements fall in the periodic table, if you want to think about it like that, sodium has a +1 electronegativity, and chlorine has a -7 electronegativity. And therefore, for one chlorine atom at the center, you get 6 sodiums bonding to it. And when they bond in this way, they form this kind of cubic structure here, okay? Where the chlorine is bonding to just one sodium in this case, but you have to imagine that this cube is repeating out in all directions. And so each chlorine in the subsequent crystal is attracting one of the sodiums, okay? And so you get basically a cubic structure here that's bonded to another cube, that's bonded to another cube, another cube, another cube, another cube, another cube. And so as that builds out, it retains a cubic structure made up of smaller cubes, if that makes sense. So that's the basic building blocks of atoms and compounds. And this leads us right into what is a mineral, okay? So minerals are chemically distinct compounds that repeat. And there are other things too that make a mineral, and I'm going to go through those. But to start, let's say, to be considered a mineral, a substance must occur naturally, so occur in nature, not in a lab. It must be inorganic, that is, it's just made up of components that are not organically sourced and can be sourced directly from mantle melts or magmas or some other process in the rock cycle. And they have to be solid at standard temperatures and pressures. So the temperatures and pressures that we see on the surface of the Earth, that is basically 25 Celsius and at 1 atmosphere of pressure. So they have to be solid at standard temperatures and pressures on the Earth's surface. Okay, and so here's some examples. So this is solid here. This is naturally occurring, and it's inorganic. So this is calcite, but this is calcite not sourced from plankton shells and things like that, but from actual calcium carbonate in mantle sourced magmas that, when cooled, forms just calcium carbonate. Minerals must also possess an orderly and repeating internal structure, and that's what I was just talking about with the halite. You have the basic building block of a halite, which is one sodium, one chlorine. But then as it starts to bond with, as like each one of those chlorines, or each one of those sodiums rather, starts to bond with another chlorine nearby, it forms these cubic structures, and that will repeat and repeat and repeat. So that's an orderly and repeating internal structure or crystalline structure. But then we also have definite chemical compositions. So a mineral has to have, in order for like halite, let's say, to be halite, it has to have a sodium and a chloride, and then another sodium chloride next to it, and those form these, these repeating structures. But that basic building block or unit cell has to be sodium chloride for that mineral to be halite. Otherwise, it's something else. So there's an internal ordered structure, it's cubic, and so as it's small cubes building up to larger cubes, this is what it would look like at the mesoscale or in hand sample. And then we also have specific chemical compositions, so sodium chloride, but there are times when you can get another cation that has a +1 that's not sodium sneaking into that repeating pattern and substituting itself for a sodium, but it's, let's say, magnesium or some other +1 cation. And that is why minerals will oftentimes be different colors, because it has a different cation being substituted in for the sodium in this case. And as that repeats, because there was more of that other cation in that magma as it was cooling, it will pull more of that cation in. And so now it's not chemically pure, but it's still mostly sodium chloride. It just has other cations occasionally appearing in the crystals that are bound together in that repeating framework, and that'll give it a slightly different color. That's why, again, minerals have lots of different colors even though they're the same mineral. So in this case, crystal structure and chemical composition are kind of the keys, whereas color, not so much an identifier all the time. And lastly, minerals must be homogeneous, okay? So homogeneous means made of the same thing. And so in this case, when you have halite, it has to kind of all be halite. It can have other, like I say, interstitial cations here and there in the crystal structure, but for the most part, it must all be sodium chloride. Once you get things that are made of many minerals, so heterogeneous, not homogeneous, that's when we get rocks. And one thing to say about rocks is that rocks can, and we'll talk about this when we get to rocks can be made of a single mineral. In the case of limestone, rocks can be, that particular rock can be made of just calcium carbonate. Or a rock can be made of multiple minerals. Here we have a granite, and that granite is made up of biotite, which is in your mineral kit, feldspar, which is in your mineral kit, and quartz, which is also in your mineral kit. And so that makes up a rock. And rocks are made of different minerals or single minerals. And then sometimes rocks can be made of other rocks. In this case, we have maybe a chert here or a microcrystalline quartz. Maybe we have a feldspar here. Maybe we have a basalt here. And these rocks all formed probably in a river system. This is a sedimentary rock. And so it makes another rock called a conglomerate, and that's just made up of other rocks. Okay, so here's a rock made of just one mineral. Here's a rock made of multiple minerals, and here's a rock made of other rocks. So in summary, to be considered a mineral, a substance must occur naturally, be inorganic, be homogeneous, be a solid at standard temperatures and pressures. It must possess an orderly and repeating internal structure, and it must have a definite chemical composition, although that does vary from time to time based on inclusive or interstitial elements that find their way into the repeating chemical structure. So let's talk about whether some of these substances that I've listed below are minerals or not. So based on the criteria I talked about in the last slide, let's look at each one of these. So cubic zirconia, which is a lab-produced zircon mineral that mimics the crystal structure of a diamond, which is just straight carbon. But because it's produced in a lab, not a mineral, okay? Because remember, minerals must be naturally occurring. Then we have coal. Coal is a rock but is it just a mineral? Well, no, because coal comes from organic material, mostly plant-based material formed in ancient swampy environments. And because it's organically produced, it's not considered a mineral. It's considered a rock. Then we have oil, also formed from organics, but not on the continents, but rather in the ocean. Not a mineral because it's, again, organically produced, not inorganically produced. Then we have volcanic glass, which is in your mineral kit. Or in your rock kit, rather. It's a rock. It's that kind of black, almost plastic-looking mineral. If you watch Game of Thrones, this is dragon glass or obsidian. But volcanic glass does not have a repeating crystal structure. It cooled too quickly because it's usually lava that runs into water. So it cools immediately, and that doesn't give the atoms enough time to organize themselves into crystal structures. So not a mineral because it doesn't have a repeating crystal structure. Then we have marble. Marble is basically metamorphosed limestone and therefore is sourced from organic materials because limestone is sourced from calcium carbonate from shells in marine environments, so not a mineral. And then we have gold. Well, gold is, let's see, gold is a single atom, right? It is, namely gold is the single atom there, right? Gold is an element. So it's made of a single atom. It doesn't have a repeating crystal structure per se because it's only one single atom, right? So it's a metal, and we consider it a mineral in most cases. But when it's a single element, right, not a repeating crystal structure, it doesn't have, gold and hydrogen or gold and sodium or gold and iron or something like that, or gold and oxygen, right? When it's just a single element, we call it a native element. So if ever you hear like native elements, native gold, native copper, that's chemically pure in that, like in the UP, when you mine for native copper, you're looking for just a bunch of copper elements coming together to form copper metal. We call that native copper. And as I hinted at before, minerals form in different parts of the earth, and most minerals have structures and chemical compositions that reflect those conditions, okay? And this is mostly determined by temperatures and pressures. Some minerals love to cool and become a solid from a magma at high temperatures and high pressures. And that has to do with the activation energies of the bonds that are formed between the different atoms that make up the crystal structures of those minerals. And some like to form at lower temperatures and pressures closer to the surface of the earth. So here we have two such elements. Here we have a basalt, or a more, it's maybe not a true basalt, but it's a mafic rock, and it's made up of things that like to bond at higher temperatures and pressures, magnesium, iron, things like that. And then also we have on the left here a granite, which is mostly quartz and feldspar and some biotites, maybe some pyroxenes or hornblends, and those like to form at medium to lower temperatures and pressures. And so they cool closer to the surface of the earth as opposed to deeper in the crust or in the mantle. So here's something illustrating that. So here we have the very outermost part of the earth, the crust, and that continental crust is made up mostly of granites. Then in the oceanic crust that have deeper temperatures and pressures, higher temperatures and pressures, I should say, we start to get basalts. And then in the mantle, we have even higher temperatures and pressures, and we'll get something like peridotite, which was in your first lab that we did. And that's what this is, where it has lots of magnesium-rich basalts and then magnesium-rich minerals, in this case that green, which is olivine. And then at the core, we'll get something that looks even more like a super duper mafic rock. And in this case, we have this core rock here, which is basically iron and nickel. And so these are different minerals that form at different temperatures and pressures. And by form, I mean solidify out of melt product or mantle or magma, however you want to think about it. We have diagnostic features, which I talked about a little in lab, but for those of you that miss lab, this will be particularly important to you. The way that we tell minerals apart are based on different diagnostic features, and this is all related to their geochemistry, all the stuff I just talked about. The first one is how their crystals form or grow as they're cooling in a magma. And that crystal form is the external expression of the arrangement of those atoms. So remember I talked about halite being cubic, and we saw that in its internal structure. The same is also true of this guy here, which is a fluorite. This fluorite it's a sulfur mineral and has some fluorine in it, and it forms cubic minerals from time to time, depending on the conditions it grew in. And so it has that repeating structure of a cubic atomic unit cell. And so in the mesoscale or in a hand sample, it looks cubic. You can have crystals that form these kind of prismatic features. You can have a dodecahedron. This is a garnet. That garnet forms these dodecahedrons, kind of looks like a D20 from like a D&D set, where it has like 20 sides. And its crystal structure looks like this. So as that crystal structure repeats out, it looks like this. And then we can have something that's octahedron here, also a fluorite, and it forms in this kind of like 8-sided structure that looks like sort of two pyramids with their bases stacked together. And that's because its internal structure looks like that, right? It's internal crystal structure at the atomic level. And so it repeats out in that same pattern. We can also get luster, which is how light is reflected off the surface of a mineral. Diamonds have a high luster, that is, it reflects a lot of light. You can get a metallic luster, right? So that's where it looks like a metal, it looks like almost a mirror. So metallics are opaque and reflect light. Diamonds are translucent and reflect light. Both have a high luster, but here we would say this is a vitreous high luster. Here in the metal, we would say that's a metallic luster. And then you can get certain minerals, like this one down here, this kind of soapy mineral that you have in your mineral kits, that have a dull luster. They still reflect light, but they don't reflect it the same way. It doesn't flash at you. It more just kind of lights up. We also have color, and like I said, color is not a good indicator, mostly because what makes a mineral is its chemical composition and its repeating internal structures. And in many cases, other elements can kind of sneak in there and change the color. Every mineral you see here in this picture is a quartz, right? Now, if we look at the crystal structure, we see that it terminates in this way. It doesn't have any cleavage. It has a similar luster between each one. These are all quartz, but some have some calcium in them, some have some aluminum in them, some have some potassium in them, some have some iron in them that give them these different colors. So color is one diagnostic feature, but it's the most unreliable, I would say. What's more reliable is streak. And what happens with streak, those of you that were in lab yesterday are familiar with what streak is, but for those of you that weren't, when you take that mineral and you streak it across a ceramic light colored plate. That mineral, if it's softer than this plate, will break up and leave behind crumpled up residue, and we call that streak. And different minerals have different streaks, and what you're getting here is sort of the pure mineral as it's breaking up. So on the outside of a mineral, oftentimes it's oxidized because it's been reacting. The outermost layer has been reacting with oxygen in the atmosphere, and so it will give it a different color. But when you streak it, you're getting the unoxidized innermost, or not innermost, but inner layers just outside of the oxidized layer, just inside the oxidized layer, I should say, and that leaves behind this streak. So different minerals have different colored streaks, and that's one way you can tell which mineral is which. You also have hardness. In a mineralogy class, we give all the students a kit like this that has a little sample of each of these, and they have definite hardnesses. This is called the Mohs hardness scale. And you could take a mineral, let's say it scratches talc but doesn't scratch gypsum. That means it falls in between a hardness of 1 and 2, and that can help you diagnose it. Similarly, it might scratch a topaz but will not scratch a corundum, or that corundum scratches it. And so it falls between an 8 and 9. It could be an 8.2, 8.7, 8.5, whatever. And so it falls somewhere in between there, and we would use that as a hardness tool. For our class, what I'll provide for you is glass, a pocket knife or a nail, a copper penny, and your fingernail. You'll provide that. And you can try to scratch or be scratched by different minerals to try to get a hardness of greater or lower than 5, in between 3 and 5, above 3, lower than 3, in between 2.5 and 3, or lower than 2.5, etc. And that'll help you narrow down some of those minerals should you choose to use this feature. Then we have cleavage, which is probably the best way to tell a lot of minerals that look very similar apart. And what is cleavage? So cleavage in a mineral is the tendency of a mineral to break along planes of weak bonding. And we define cleavage as being perfect cleavage, that is well-defined, nice, pristine cleavage faces, or poor cleavage, right, where it sort of breaks along those bonds, but it also fractures a little. And cleavage often happens in more than one direction, and so therefore you'll have two different cleavage planes that are not parallel. And since they're not parallel, that means they intersect at some point. Now that might not be in the hand sample, they actually intersect, right, where you have a corner. But you might sometimes just have two cleavage planes exposed on a mineral, but they're broken, before they can intersect with each other. That part of the rock, that side of the rock, or mineral rather, is broken. And so when that happens, you kind of have to imagine that cleavage plane continuing out past the broken point, and measuring the angle where those two cleavage planes meet. So what does that look like? So the brown atoms in this figure are bonded with the blue atoms in this figure, and they form a sheet, right? So these brown atoms and these blue atoms are bound together, and they form one like sort of element thick, but almost infinite elements wide. And so they form this like really thin atomic sheet. And those sheets are joined by these bonds of other elements that find a spot in this sheet that has some kind of a charge. They like that charge, and so they bond to it. And if they have, let's say this sheet here, in certain parts exerts a -1 charge, just based on the way these elements are configured. And this sheet here, similarly, has a -1 charge at certain points in its atomic structure. And then some +2 cation comes along, right? And it's like, well, I'll bond to this atom here, but I'm a +2. This is a -1. Here's another -1. I'll bond that together. And then somewhere else in the crystal structure, another +2 bonds with a -1 and -1. And so it loosely bonds these sheets together, right? Well, when I exert a force on that, like bashing this mineral with a hammer, it's going to break these bonds, but not these, right? Because these bonds are strong. They're awesome. Where they're not awesome, they're being bound together by these guys. And so when I break it with a hammer, I'll break these middle bonds, but not the sheet bonds. And so that mineral will cleave along this plane and break into smaller sheets. And that's what this looks like here. This is a biotite. When it's bound together by these weak, in this case, hydrogen bonds or van der Waals bonds, it's clumped together as one thing, but as soon as I exert some pressure on it, it's going to naturally break along these thin sheets here. That's why micas, in this case biotite, which is a dark mica, forms really thin sheets when you break it up. So cleavage is based on the number of angles or number of planes and angles. In this case, with that mica I was just talking about, we've got one single plane that it cleaves on, and we call that basal cleavage. And that's a mica there, so there's that basal cleavage. We also have prismatic cleavage, which is two planes, and those planes can be at a right angle, right? That is 90 degrees from each other. So this plane here is 90 degrees from this plane. And this middle plane in yellow here represents this top that we're looking at here. That's that plane of cleavage. And then this purplish plane here represents this side plane that we're looking at here. And you'll see that the overall mineral makes this kind of rectangular shape. But then if you look deeper into the mineral, you get this kind of stair step, which is still those same planes being expressed. Okay? And that would make sense since the internal atomic structure is that repeating pattern. So you could break this up into smaller and smaller pieces and still get that same shape, or you could break sides of this rock or mineral and still get that same shape. And there's one there. That is a pyroxene or an augite or a feldspar. All have the same prismatic morphology or shape. You can also have prismatic ones that are also two planes, but those planes are not at 90-degree angles or not at right angles. And these form sort of rectangles that are slightly skewed into different orientations that generally form 60 degrees and 120 degrees. So take a right angle and make one slightly oblique or sort of bend one away. Everything will still add up to 180, but in this case now you have 120 here and 160 here. And those form minerals that look like this. This is a hornblende. This is also in your mineral kit. And it is, once you find the cleavage planes, you'll notice that it has a 60-degree cleavage plane in one spot and a 120-degree angle of intersection between two cleavage planes at another spot. Also, we can have cubic. That's the halite I showed you. Here it is. And this is one plane in this direction, right? That represents this top face. So it's parallel to this yellow plane that we're showing here. Then you have this purple plane, which is parallel to the side here. And then you have this blue plane, which is parallel to the foreground plane here that you see. So this is three planes, so three cleavage planes, and they're all 90 degrees from one another or perpendicular from one another, okay? And if you go into the PowerPoint, you should be able to rotate this around. Otherwise, I think I have a link somewhere in the PowerPoint, you can like manipulate these different crystal structures and rotate them around. But for cubic, you have 3 planes of cleavage, all at 90 degrees. Then you have rhombohedral, which is 3 planes of cleavage again, where you're seeing cleavage planes on every side of the mineral that you look at, but they're not 90 degrees from each other. They're bent in some other way. And these form a rhombus, which is a 2-dimensional object, projected into 3 dimensions. We call that rhombohedral. And in this case, we have a calcite, which, as you'll remember, reacts with hydrochloric acid when you're looking for it in your mineral kit, but it forms this sort of rhombohedral shape. And a lot of calcite is rhombohedral. It's one of the kind of main identifying factors aside from the reactivity with hydrochloric acid. Then we also have minerals that have 4 cleavage planes. In this case, we have a fluorite here on the left. And it's basically, like I said, 2 pyramids with their bases stacked together. So we have 8 sides, but remember, the cleavage plane here is the same cleavage plane as this one down here behind, that's sort of resting on the table here, which you can't see. And so because this plane and the plane behind, like sort of kitty corner from it, is parallel, we would call that one cleavage plane. And so if we have 8 sides and each side corresponds to another cleavage plane that it's parallel to, in this case we would have 4 cleavage planes. And that's not perfectly denoted here because we only have, 3 symbols, but they're just not pointing to all the sides here. But this gives you a sense of like this circular side here, or this side denoted by this oval, corresponds to this side denoted by the oval as well. And the relationship between the internal structure of a mineral and the cleavage is that sometimes the internal structure of a mineral is so strong, in the case of quartz, that we don't get cleavage. So quartz is a silica oxide, right, or a silicate, as we call it, and its bonds are the strongest. It's just a bunch of silica bonded to a bunch of oxygens, and those oxygens are shared between different silica, so they make what we call a tetrahedron, and they don't want to break, and they often don't have any of those smaller cations or anions that are bonding the major parts of the crystal structure together. Okay, so they don't break along any preferred orientations because they're really just they're really bound together very strongly across the whole mineral. And in this case, like I say, minerals tend to cleave between the silicate structures, and since quartz is all silicate, it tends to not have any cleavage, right? Just fracturing. So you can still break it, you can still break the bonds, but when you break the bonds, it breaks in all kinds of different places, and so it doesn't form one single nice cleavage plane. Okay, if you see a nice straight flat plane in a quartz, which we see all the time, that's actually its crystal form, not its cleavage plane. So again, fracturing is how a mineral breaks. And so this is a mineral, quartz mineral that's been broken, and you'll see that there's no flat planes. It's what we call almost conchoidal. So it's just broken in all manner of ways here, and so we call that fracture. Another diagnostic property, now that we're moving out of cleavage, is specific gravity. And that's the ratio of the weight of the mineral and the volume of a mineral. And we did this with basalt and granite. You basically weigh the mineral to get its mass, and then you drop it in a graduated cylinder to get its volume. And you can divide those two against each other, and you can get the density. And we call that also specific gravity. So those two terms are interchangeable, but that is the density. And all minerals have different densities. This is a great way to figure out the mineral that you're trying to identify. I really encourage you to incorporate this into your diagnostic repertoire and use specific gravity during the mineral test. So I'll have scales and water and stuff out for you. So most rocks, because they're made up of different kinds of minerals, they tend to have average densities that fall within the range of about 2.5 to 3. Now you guys got lots of different measurements for the granites and the basalts in that first week activity, but what you should have gotten, if we take an average of all sort of granite samples across the planet and all basalt samples across the planet, granites tend to fall about 2.5, 2.6. Basalts tend to be about 3, 3.1, 2.9, 3.2, something like that. So they fall within this range. Whereas minerals, because they're chemically pure mostly, they can have very specific densities or specific gravities. That's why we say that. So the density of rocks or the specific gravity of rocks tends to be an average, whereas for different minerals or native elements, we tend to get very specific numbers here. So in the case of galena, which is a sulfide mineral, you get 7.5. In the case of gold, you get a heavier sort of, because gold is heavy even though it's soft. So that's why we like it. It's very useful for lots of different things because it is heavy and also soft. Juxtapose that to aluminum, which is light and hard, right? So those different native elements or native minerals, i.e. metals, have very specific densities. And so that's one way you can absolutely identify a certain mineral. Some other things that we talk about, taste. I don't recommend you necessarily licking the samples in the mineral kits because they've been probably licked before. But if you don't care about germs or you feel like your immune system is tip top, go ahead and dab your tongue on a cubic light colored mineral to see if it's halite, because it will taste salty. Also, there's feel. So does it feel chalky? Does it feel slippery? Does it feel rough? Does it feel extra smooth? So sometimes just those tactile things can help. Is it magnetic or not? So there's a mineral or two in your mineral kits that are metallic. One's highly metallic, one's slightly metallic. You could use that to help tell some things apart that are very similar as far as appearance and density. And then also you can drop diluted HCl on it. That'll be available to you during the test and in lab when you're doing your IDs. And when you drop that hydrochloric acid on it, it will fizz. And the one here that's very important is calcite or calcium carbonate. It is in its mineral form, it is calcite. In its rock form, it is limestone. And when you drop HCl on it, it forms CO2 gas, and that gas will bubble away out of the solution. So you'll see it's a very conspicuous, sort of obvious bubbling. You'll know it when you see it. If you don't see it, it's not bubbling. If you definitely see it, it's bubbling. So this is the part of lecture where we would normally stop, and I would introduce you to the different minerals in your kit, but a lot of you did that yesterday, and so we'll just move on. So let's talk about the way that we group minerals. So again, like I said, most minerals are reflective of the conditions under which they form. So the temperatures and pressures under which they form. And for the silicate minerals, that is minerals that have the basic building block of silica and oxygen, we divide those into two groups. The darker minerals, which is sort of a vague term, but they are actually darker in color, and the lighter minerals. And for the darker ones, we call those ferromagnesian, which means they contain iron and magnesium, and the non-ferromagnesian, which means they don't contain those things, or they contain them in very trace amounts. Most common minerals are made up of silica, like I said, and oxygen, but also aluminum and oxygen and iron. These are the most common elements on Earth. They make up most of the crust and most of the mantle. These are the 4 most common elements on the Earth. And minerals are classified by chemistry based on their anions or ion groups. So any oxygen plus a metal, we call that an oxide. So iron oxide, copper oxide, nickel oxide, etc. If you have a sulfur plus a metal, so iron sulfide, copper sulfide, we call those the sulfide groups. Then if you have minerals with an anion group, so anion groups, we call these compound anions. So when you take, for instance, a carbon and 3 oxygens and bond them together, the resulting charge is a -2. So this whole thing acts as an anion, as though it were a single element with a negative charge. Okay, so this is a carbonate, right? So when that bonds to, let's say, a calcium, calcium has a +2. A carbonate has a -2. When they bond together, they form calcium carbonate or calcite. So that would fall in the carbonate group. And then sometimes we have that same compound anion, and it's a silica with a bunch of oxygens, and that has a -4, so we call that a silicate. Okay. So let's start with the silicates. Silicates are the most common and important minerals on Earth. Quartz down here is a silicate, and it's a pure silicate. It's pure silica and oxygen, okay? And silicates are made of silica and oxygen with or without metallic elements. So once you start to add metallic elements in to that crystal structure, then we start to diverge away from quartz. But quartz is kind of the baseline. It's silica and oxygen, SiO2. For the silicate group, like I said, the basic building block is silica tetrahedra. Okay, so a tetrahedra is a silica with 4 oxygens. That makes that silicate compound here. And what we have here is this little tiny silica atom rather, in the middle, surrounded by 4 oxygen atoms. Oxygen atoms are, they have more electronegativity. They're bigger, right? If we had a periodic table in front of us, I'd show you the atoms get bigger as you move to the right. So a combination of this charge plus the interstitial space this atom can fill in between this clump of 4 oxygens means that those things can bond together. And so this silica bonds with the 4 oxygens and forms the basic building blocks of a silicate, SiO4. Oxygens can be shared by different silica atoms. So you could have, if you think of the picture we just saw in the last slide, you could have a silica bonded to just 4 oxygens, and so it's just a silicate all by itself, right? It's a little silica tetrahedra all by itself. But as things are cooling and starting to form solids, you can also get a silica that's bonded to an oxygen, but that oxygen is also bonded to another silica, and so those 2 silicas will pull in 3 more that are unbonded, or 2 more that are bonded and 2 that are unbonded, or whatever. And that's how we get these crystal structures. They form different structures. In this case, over here on the left, we see a silicate chain where this silica is bonded to an oxygen down here, an oxygen down here, and an oxygen facing us, sort of out of the page. And then it's bonded to this oxygen here, which is also bonded to this silica, which has two silicas bonded to it, and then it's bonded to another silica that's shared with another silica, an oxygen shared with another silica, and so it'll form these chains, okay? And this is a single chain, which is one of your minerals in your mineral kit. So the way we categorize silicates are based on the number of oxygens bound to other silicas in the crystal structure. And if you have just a single silica tetrahedron here that's bound to other single silica tetrahedrons or silicates by some metal, usually magnesium or iron, and you can think of that like there's an iron that's real keen to bond to the somewhat electronegative bits of the oxygen that's left over from this bond. There'll be an iron kind of in this space here, and then another single tetrahedron bound to that. That pattern will repeat and repeat and repeat out, and we get this lovely green crystal here called an olivine. And it's kind of the most basic silicate. Okay. Then you have the pyroxene group that is formed by these chains where one oxygen is being shared between two silica, and then that repeats. There's one oxygen being shared there, one oxygen being shared there. It forms this single chain, and then those chains are bound by, again, magnesium and iron. So just think like a chain, and then some metal, and then another chain bound to that, and then a metal, and then another chain bound to that, single chain, and that's the pyroxene group. And this is a pyroxene up here. It's in your mineral kit. I think it's number 6 or 7. And it's differentiated by its kind of cousin, or maybe even brother or sister in this case, the double chain. The double chain is denoted here. This is what the crystal structure looks like. And this is where it's sharing 2 oxygens now. Each silica is sharing 2 oxygens, one with the silica next to it and one with the silica next to it. And those double chains are bound by metals, again, iron and magnesium, but also calcium in many instances. That forms the amphibole group. In your kit, this is called a hornblende. It's right next to the augite or augite, which is your single chain pyroxene. And the way to tell those apart is the cleavage angles, and that has to do with the configuration of these chains and the metals that bind them together. Form either two cleavage planes with 90 degrees or 2 cleavage planes with 60, 120. Then we have these double chains sort of building up to the next level where they're sharing most of their oxygens with each other, but not all. There's going to be one oxygen out there not bound to the silicate. Well, it is bound to the silica, but it's not bound to another silica next to it. So it has a charge, it has a negative charge. So again, it wants to bind with some metal if there's metal available in the magma as it's cooling. Again, magnesium and iron are very common, but also potassium and aluminum. And this forms the mica group, or the sheet silicates. And then we have silicas where all their oxygens are bound to another silica next to it, forming this interlocking 3-dimensional network that we call a framework silicate. And those are your feldspars, of which we have 2. One is orthoclase, or potassium feldspar, which has potassium in its crystal structure somewhere, substituting for the silica atom in some instances. And then the plagioclase feldspar, which has calcium or sodium. And then both of those also have aluminum in their crystal structure. And those both have 2 planes of cleavage at 90 degrees. The best way to tell those 2 apart is here we have potassium feldspar on the left and calcium or sodium feldspar, which we call plagioclase, over here on the right. And the most distinctive thing here is where you can use color as your indicator. So both have two cleavage planes at 90 degrees, but the calcium, or the potassium feldspar rather, is going to have a pinkish color. Sometimes it's green, which is amazonite, which is another type of orthoclase or potassium feldspar. All of your potassium feldspars or orthoclase in your kit will be either green or pink, pinkish orange. And then your plagioclases tend to be white or gray or sometimes a bluish color. And there's some other things that you can use to tell them apart, namely their perthitic texture, which I'll talk about. But those are the feldspars, very common in lots of rocks. Granite's full of them. Gabbro has lots of orthoclase. So they kind of run the gambit between your mafic and felsic minerals, which are rocks, which we'll talk about when we get to igneous rocks. And then also you have just straight up pure on silica oxide, right? Or SiO2. And that's where basically all four oxygens in the tetrahedra are bound to other ones. And so if you take an average, if every single oxygen in the tetrahedra is bound to another silicate, you basically consider each oxygen being half bound to one and half bound to another silica. And so if you have four atoms surrounding the silica, each one being half bound to another silica, then when you take the average or the half of that bond and you get 2. So SiO2 is the chemical formula for quartz, and it has no other metals in its crystal structure. And so it tends to, in its purest form, look like this over here on the right, or it can look like this over here on the left. This is a crystal that was allowed to grow. This is just a bunch of silica tetrahedra that was bound together by some other process besides just slow growth in a magma chamber or hydrothermally. And it can have other metals in it here and there, which we call interstitial or inclusive metals, but those aren't part of the actual crystal structure of the mineral. They're actually just, they just pop in here and there and substitute for a silica every now and then, and that's where we get the amethysts and the citrines and the smoky quartz and stuff like that. So going into a little bit more depth, here again is an olivine, and that's got the isolated tetrahedra. So SiO4 is the root of its chemical formula. With the single chains, the SiO3 is the root of their formula, and that's because only one oxygen now is being bound by another, or being bonded to another silica. So it has three, it has, this is a tricky one. It basically has one unbound here. It has one unbound oxygen here. And then it has two that are half bound. So that adds up to 3. 1 plus 2 halves makes 3. And this is what it looks like in thin section. I'll bust the microscopes out. You guys can look at some thin sections. But this is what it looks like in hand sample. And it's 2 cleavage planes with that 90 degrees there. That's an augite. Here's that double chain. It has, let's see here, let's count. 1, 2 unbound, and then 1, 2 half bound, again making SiO3, right? And because it's a double chain, it just has a slightly different crystal form, and so the cleavage planes here, there's 2 again, just like in the augite, but in this case they're not 90 degrees, but 6120. Then we have the sheet silicates again. Now these are, let's see how many it's sharing. We got 1/2 share here, 1/2 share here, and then no second binding to this oxygen, no second binding to this oxygen. So this is also SiO3, but it's going to be bound to a bunch of metals. So the crystal formula is going to be some metal like aluminum or calcium, and then SiO3. And then the framework silicates, they have an SiO2 here's quartz, here's a plagioclase feldspar, and here's a potassium feldspar. Potassium feldspar and plagioclase feldspar both have cleavage angles, both at 90 degrees, but the way to tell them apart is by color in this case. So pinkish orange or green in rare cases is your potassium feldspar. Bluish, gray, or white, that's your plagioclase feldspar. And then potassium feldspar also is going to have these kind of stripes here, which we call lamellae or perthite. And then your plagioclase feldspar also has certain properties that you can use to tell it apart, namely a thing called sometimes called play of color or iridescence. And that's when you move the mineral, you rotate the mineral in a light source, you'll get these sudden flashes of these really brilliant blues and purples. And again, I want to show you this because I want you to notice the pattern here. So as we move down the list here, at the very beginning, we've got these kind of low isolated tetrahedra or olivines here. And then as we increase in order and complexity, we end at the framework silicates, or what we call, like kind of high silica, because this is going to have more silica in it than this, okay? Because remember, each one of these single tetrahedrons in an olivine is bound by metals. So there's lots of metal on each one of these oxygens binding it to the next tetrahedra. Whereas here, you have little to no metals in the mineral. So generally, there's way more silica in the feldspars and in the quartz than there is in the olivine. And then in this kind of intermediate group here, you've got more or less metals based on whether it's a single chain, double chain, or sheet silicate. And like I mentioned, to complete the silicate structures to produce the different groups, you need cations, right? You need metal cations to jump in there and bind those tetrahedra together, or bind those chains together, or bind those sheets together. And the most common ones in the minerals that we're going to be looking at are iron, or Fe, magnesium, or Mg, potassium, or K, sodium, or Na, aluminum, or Al, and calcium, also Ca. And these, if you've ever wondered why Fe is iron, it's because the Romans called it ferrium. So we go by the Roman names because back in the day when scientists fancied themselves really fancy after the Dark Ages, they borrowed from a lot of the Latin, which was seen as kind of the golden age of civilization in the West anyway. And so they borrow a lot of Latin names. This is probably no surprise to you in science. And so a lot of these chemical notations are based on the Latin names. So some of the names themselves are based on the Latin names, but some are changed. When they changed to English, we went from ferrium to iron, and so on. And one thing to note here is each one of these different cations, whether it's silica, aluminum, iron, magnesium, iron 2, or sodium, calcium, potassium, they have different sizes. And when they're different sizes, they're only allowed so much space within an oxygen. So this changes the way things cleave. This changes the shape of the mineral overall, because you can have tightly packed tetrahedra, or you can have loosely packed tetrahedra, and so on. So something to keep in mind. So in summary, the basic framework of a silicate is that it's a tetrahedra formed by a single positively charged silicon atom, surrounded by 4 negatively charged oxygen atoms. The tetrahedra can be linked to each other by sharing oxygen to form a variety of silicate structures. And then those structures can be linked by positively charged atoms or cations like calcium, sodium, potassium, iron, and magnesium, etc. So some basic properties of the ferromagnesium silicates. They usually have magnesium or iron in them, so they're dark in color and they're heavier. So they have a higher specific gravity, they're denser. Olivine is one such. It's sort of the textbook ferromagnesium silicate. It cools at high temperatures, so it likes to be solid earlier in the cooling process. It'll become a solid way before anything else. It's kind of the first thing to precipitate out of a liquid, a magmatic liquid. So it forms at high temperatures. It's black to green in color. It often has a glassy luster. It has no cleavage. It has lots of fracturing, and it's sort of grainy or sandy looking. You can get just good old regular olivine crystals, which form these kind of beautiful crystals here. But oftentimes those are really, really small, almost the size of grains of sand. And so when you're holding an olivine chunk in your hand, a lot of times it looks like a green sandstone, or it has that same kind of texture as a green sandstone. Sorry if there's a volume change here, but I had to switch to a different microphone. But moving right along, the next ferromagnesium silicate we have is that single chain silicate, and that's pyroxene, also known as augite in its most common form. It's dark green to black. It's opaque. It has two cleavage directions at 90 degrees, as seen here. Get my laser pointer. So yes, so here we see a cleavage plane here, and then a cleavage plane here, and then the corresponding parallel cleavage plane there and there and there. So so even though it's got four sides, it's actually two parallel planes, or a group of two parallel planes. And so we say there's two cleavage directions, and and they intersect at a 90-degree angle. Then we have hornblende. It's also dark green to black, and it's also opaque, and it also has two cleavage planes. However, this is the double chain, so it's bound together slightly differently with those metal cations holding all the tetrahedra together, and so this forms this kind of 60-120 angle. Then we have the micas. So the first one is the darker mica, and that's it's called biotite. And I just remember biotite starts with a B, black starts with a B, biotite's always black, pretty much. So so biotite is black, and that usually helps me. Sorry, my cat's freaking out. And it has perfect basal cleavage, so just one cleavage plane because it's a sheet, right? It's almost two-dimensional. So it has that one cleavage plane. And then we have, oh, okay, I guess I didn't do muscovite next. Then we have garnet. Garnet lacks cleavage. It has a glassy luster. It fractures conchoidally. So sometimes it can just look like a chunk of broken, it almost looks like a really, 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 really deep red fractured quartz. It can be like deep red to purple in color. But when it's allowed to grow as just a straight up crystal, you often get this like D20 sort of dodecahedron shape. Looks like a 20-sided dice. Then we have the light or non-ferromagnesian silicates. In this case, now there's almost no iron or magnesium in these minerals, and these are where we start to begin the framework silicates. They tend to be lighter in color. They tend to be lower in density. They tend to have lots of calcium, aluminum, potassium, or sodium in them, and these are your feldspars. And again, this is your potassium feldspar here on the left, often pinkish orange to green in color. And then you have plagioclase feldspar, and that is going to be gray, blue, or milky white in color. Here are the two types of potassium feldspar, and in geology, these minerals have tons of names. They're all interchangeable. Find one you like and stick with it. that's my advice to you. A lot of people say potassium feldspar, or for short, they'll say K-spar, which is potassium feldspar, the K being the chemical symbol for potassium. And then we just drop the feld and just say K-spar. I say K-spar. But other people will call it orthoclase or microcline. And they, again, tend to be this creamy salmon color, or they can be an aqua green color. They have two directions of cleavage, both at 90 degrees to each other, and they have these exsolution lamellae, okay? And that's this like striped color that you see, and you can see it in the green variety as well. And this is because as the mineral cools in a magma chamber or in a metamorphic zone, your potassium will preferentially separate out from any other cations that might be in there, maybe a little bit of sodium, maybe a little bit of aluminum. And so it forms these kind of striped bands where there's more potassium and then more of another cation. And so that's sort of a dead giveaway for K-spar. For the plagioclase, we've got this white to gray coloring over here. Sometimes it can be bluish. Again, two directions of cleavage. They intersect at 90 degrees. Often they have striations, which is another type of parallel striping. But you get this beautiful iridescent play of colors that I mentioned in this variety over here, which is a plagioclase feldspar known as labradorite. If you look at it spelled, it literally spells Labrador, like the dog, and then ite, or Labrador, like the island, I guess. And when you move it around or rotate it in light, you'll get this like sudden flash of blue and greens and sometimes kind of orangish colors. This is very common in countertops. You see this a lot in gravestones. It's a really beautiful mineral. I'll bust some out so you can see that play of colors. I don't know if many of your kits have it. Some of them might. So if you are one of the lucky people who grabs a kit that has this play of colors as you're looking at your plagioclase, which is number 1 in your kit, by the way, be sure to show this to other members of the class. Finally, we have the framework silicates. In this case, the most pure form is quartz. It does have certain inclusions in it of metals that give it different colors, but these are all quartz. This is a smoky quartz here in the bottom right, amethyst or a purplish quartz in the left, kind of pure quartz up here on the top left, and then citrine up here in the top right. And all are SiO2, but then they'll have minor metal inclusions depending on whether there was metal available in the magma at the time of cooling that will give it these different colors. Other types of quartz that are important to note, and also in your kit, I believe this is number 4. Yep, pure quartz is number 3. And so number 4 in your kits is chalcedony or chert. This is also quartz, but it formed in a way where it didn't have time to grow any real crystals, so it formed really quickly. It's often translucent looking and banded, or it's opaque and gray in this kind of just ordinary sort of looking rock. Most of your friends, since they found out that you took a geology course, they're going to be like, oh, what kind of rock is this? What kind of rock is this? What kind of rock is this? And 99% of the time, it's a chert like this. People find these all the time and want to know what it is because they often look a lot prettier when they're wet. Once they dry out, they just kind of turn into this kind of gray blob. This is a lot of times if you find arrowheads or see arrowheads in a museum, it's made out of this chert. So it's sometimes called flint stone. And it is the reason it's very useful in shaping into sharp points is, again, remember, quartz doesn't have any cleavage planes, so you could basically carve this rock however you want, and you're not going to accidentally whack it at one point and the whole section's going to break off because there's a cleavage plane there. So these are really easy to carve into different shapes, although they are very hard. So not super easy, not like marble or soapstone or something like that, where you could really carve it into something very distinct. These are hard, but you can get a nice point on them. And then another light or non-ferromagnesian silicate related to the biotite, which is the ferromagnesian version of a sheet silicate in the mica family, we have muscovite. So here's a biotite up here that's got these black bits, and then the lighter colored version of that is muscovite, and it's just the other mica, and it's the white colored mica or the completely transparent mica. Other minerals you have in your kit are kaolinite, which is a soft clay chalky mineral over here on the left. You can draw on your table with it. It's chalk, basically. And then you have talc, which is has a real slippery feel. It's often white to pale green and opaque. You can scratch it with your fingernail, and when you rub your fingers across it, it feels slick or slippery like a soap. This is also sometimes called soapstone. And when you cut this on a mineral saw or a rock saw, which uses water to cool the blade as you're cutting it, it'll actually form bubbles. It has lye in it, and so it is a source of soap, what we use for soap. It is one of the active ingredients in soap is talc. And when you cut this mineral or you break it up into powder and get it wet, it will bubble and foam up like soap does. So one really important thing about minerals is their temperature of formation. And one good rule of thumb is the light colored silicates, for example, quartz, tend to form at lower temperatures, and many of the dark colored ferromagnesian minerals, like olivine, tend to form at high temperatures. And by high here, we mean greater than 1,000 degrees Celsius. So when we're talking about temperature of formation, this chart here is called Bowen's reaction series. It's GL 101 standard fare. It is what every geology or intro to geology student learns, and it's super duper important, especially when we're talking about how different rocks form. And what it's showing here is how different minerals crystallize out of a magmatic melt as you go from high temperatures up here at the top to low temperatures down here at the bottom. So above 1400 C or 1400 Celsius, that all of the magma is a liquid. No minerals have began to crystallize out yet, so it's just a kind of a stew of elements. And as you start to cool that magma, once you hit 1400 C, you start to get olivine crystallizing out over here on the left. And that's on the discontinuous side. That's because each mineral that's forming here is discontinuous from the one before it and the one after it. And on the continuous side over here, you get calcium-rich plagioclase beginning to crystallize out. And that's because the bonds that make an olivine, basically silica and oxygen, bound together by minor metals, and calcium, which is SiO2, framework silicates bound by certain metals, those reactions that are necessary for that bonding to occur happen at these higher temperatures. The rest of this stuff below it, still liquid, so it hasn't formed yet, okay? So if you have a magma that started to cool at a really high temperature, right? And then for whatever geologic reason, it suddenly erupts onto the surface, you're going to get rocks that cooled very quickly at the surface that have lots of olivine in them, because the olivine was sitting there cooling inside the crust just fine. And then all of a sudden it erupted. Then you get a basalt, which we'll talk about when we talk about igneous rocks. But that basalt has lots of olivine crystals in it. And it also has calcium-rich plagioclase. Then as we move down, so the magma is continuing to cool, the olivine is cooled, and what's left over is a certain amount of silica in the form of silicate tetrahedra, but there's less iron and less magnesium than there was when the olivine was forming, because the olivine sequestered a lot of that material. And so the next thing you get is a pyroxene, which is that single chain silicate, and it's bound together by less iron or magnesium, and that forms your augite or pyroxene. And then as we move down, we get amphiboles with even less iron and magnesium. And then we get down here where there's very little to no iron and magnesium. And that's this break here where we have biotite going to mica. Once you get to mica, you have mostly just silica and oxygen left in the magma. Most of the metals and other elements have been used up by these previous minerals and the rocks that are formed by those minerals. And so then you just have the framework silicates left over, because there's still a ton of silica and oxygen left over because they're the most common in a magma. And so that's when we get the potassium feldspars or K-spars, the muscovite micas, and then finally quartz. Quartz is the last thing to form in a magma at about 650 Celsius. And over here, here's a little preview of the rocks that we're going to be looking at when we get into rock types. And rocks that are made of mostly olivine are ultramafic. That's a spelling error there. That's a typo. It's actually ultramafic, not ultramatic. And then you get the basaltic or mafic rocks. Then you get the andesitic or intermediate rocks. And then you get the granitic or felsic rocks, which is high silica, and that's the rhyolites and the granites. So here, low silica, lots of metals, some intermediate stage, and then mostly silica, very little metal. And then let's talk about the non-silicates that are in your kit. And I mentioned this to everybody in class yesterday, but if you weren't in class, just so you know, and you can go back and look at other slides, anything that's in this blue here is in your kit. Any mineral that's in blue or any rock that's in blue, when I'm doing my presentations here, they're in your kits. So these are ones you need to identify and learn. So the carbonates, again, their anion is a carbonate polyatomic structure made up of a number of different atoms, but the result is a charge, and so it acts as an anion. And for the carbonates, we have calcite, which is this mineral here. It reacts with acid, forming CO2 gas. It often has a rhombohedral structure. It's usually pink or orange in color, but it's fairly translucent, like this one. And then we have dolomite, which is a calcite that has a little bit of magnesium in its crystal structure. It forms similar crystal habits or crystal forms where it has those rhombohedral cleavage angles, but it's got magnesium in it, so it's not clear and pretty like this one. It's actually a more milky, sort of dull color. But it both will react with hydrochloric acid. Calcite a little more quickly than the dolomite. For dolomite, if you scratch it on the plate and then hit it with the acid, it will react. So I kind of misspoke yesterday when I said only one thing reacts with acid. It's actually kind of these two. In my mind, they're both sort of calcite, so that's kind of why I misspoke there, but I don't want to confuse you. So you can get dolomite to react with acid as well. And the key distinction between the two is how translucent they are. Then we have the sulfide and oxide mineral groups. Both are in your kit. On this slide here, we have magnetite. It's black, opaque, and supermagnetic. Boom, done, easy. If it's magnetic, it's magnetite, move on, okay? If it's hematite, like this beautiful banded iron that we have up in the UP, and we have samples that I'll show you in class. We have some beautiful samples of this. It's banded because it's alternating layers of hematite and jasper, which is a kind of chert. It's usually silvery to gray, rusty brown to black, and it has that real characteristic brown, reddish brown streak that I showed you yesterday on the streak plate when I was introducing streak. And all hematite, whether it's specular hematite or it's massive hematite, it will have that. And both of those look very different, but they'll have that definite reddish brown streak. Then we have the sulfides. The sulfides that are in your kit are pyrite over here on the left. It forms these beautiful cubes, and some of those cubes are sometimes intergrown with other cubes. I was showing you guys that yesterday. Here's what that looks like when it really goes crazy. And it tends to be the more gold or yellow variety, and it often has this cubic structure, although not always. But if you look at it in hand sample, you'll see little cubes in it. That's a dead giveaway that it's pyrite. Then we have chalcopyrite, which is more gaudy and brassy colored, more of a yellowish gray or greenish kind of color. It's related to pyrite, but it has more iron in it. And so that's chalcopyrite. And in some cases, chalcopyrite can be slightly magnetic. I just wanted to point that out. You may feel a little tug of the magnet on it. That can sometimes help you if you're looking at the difference between pyrite and chalcopyrite. And then we have galena, which is also cubic, has cubic cleavage, but it's often this really, really, really bright silver color. Okay, so easy to tell apart from the pyrite, but both are sulfides. One just has way more iron in it. Then we have halite or gypsum, and these are what we call evaporite minerals because they were formed from minerals dissolved in ocean water that as it evaporated away, it left this stuff behind. And the one that has very distinct cubic cleavage and is often clear to very translucent and is a salty taste if you care to lick it, is halite, and that's NaCl or table salt in its mineral form. And then we have gypsum, which was mined here in Grand Rapids for about half a century. So there's gypsum mines under here. It can be scratched with a fingernail. It's very, very soft. It does not react with acid. And it can be either this kind of white color that's very easy to scratch, or it can be pink or orange. The Grand Rapids variety is very pink, very pinkish, orangish color, and I'll show you different varieties of that gypsum. Then finally we have graphite, which you'll see in your mineral kit. It has a slippery feel, has a silvery color. It's very, very soft. You can write on a piece of paper with it. That's why we use it in pencils, and that's graphite. Then we have limonite, which is often this kind of earthy looking yellowish brown mineral. Sometimes it's kind of a bright yellow. I think this one's very easy to tell apart in your kit from the other minerals. And we also have fluorite. Fluorite is that mineral that we saw that was octahedral with the two pyramids stacked together. It's often purple in color. It's translucent. It has those four directions of cleavage. And then sometimes you don't get those perfect octahedron shapes of the two pyramids stacked together. Sometimes you'll just see little triangular fragments. So if you have an amethyst in your kit, you will not see these triangular fragments. But if it's a fluorite, and both are purple, if it's a fluorite, if it's purple, if you look really close, somewhere in that sample, you'll see a triangle. Okay, and that's a dead giveaway that it's fluorite. And then sometimes you can get fluorite that has little bits of green in it, and that's because it was exposed to UV rays. UV rays turn fluorite into a greenish color if left in the sun long enough. So I'll finish out the lecture here with a few more slides on mineral resources. We do have a section coming up in the next week or two about mineral and energy resources at large, but I just kind of want to talk a little bit about mineral resources here and kind of the consumption of minerals So mineral resources, obviously, we're very interested in metallic minerals. And those include iron, copper, silver, nickel, and these mostly form as oxides or sulfides, so bound to an oxygen or bound to a sulfur. And when that happens, they form rocks that we call ores. And there are processes where you separate the metal from the oxygen or the sulfur or other minerals that are included in the ore. And then we have non-metallic minerals. And those include, and those include most of the silicates. And why do we like silicates? Well, we like silicates because they have silica in them. And you don't have to think too hard to think about what we use silica for. And if you Googled it on your phone, the phone that you're holding in your hand is the reason we love silica, because we make electronics out of it, silica chips. And the conditions that form economic minerals are generally they form in unique conditions. They generally occur in certain regions. They're usually finite or exhaustible. It took usually hundreds of thousands to millions, maybe even billions of years to form. So they take a very long time, and they form in very specific regions. And so they're finite or exhaustible. Like, they're hard to get and they're easy to use up. And therefore, they are non-renewable. So the formation of mineral resources. So the ore minerals are minerals with a high concentration of metals or other economically important minerals. And when we find these, we call them mineral deposits. Like over here, we've got gold in this quartz vein here. And you can get mineral deposits that are natural concentrations of ore-bearing minerals, and that's high grade, and that's usually where they formed inside a magma chamber, or they were deposited hydrothermally, and that's where water, groundwater, or any other kind of fluids that are moving through the crust get heated up when they're in close proximity to a magma chamber. And so once they're hot, they are able to dissolve things. They tend to dissolve quartz because, remember, quartz is the last thing to cool from a magma chamber. So then think about going the opposite way. When you're heating up minerals, quartz is the first thing to melt into a liquid. So it's the first thing to be dissolved. It then dissolves into the groundwater, the hot groundwater. It moves through the crust, and then as it begins to cool, it crystallizes out. And any other things that were dissolved with that quartz water, we'll call it, they also precipitate out and cool as well as a solid. And that's why we get high concentrations of metals in these quartz veins. And those veins are just cooling inside fractures in the rock. And that's how we get veins, and that's how we get ore veins or deposits. And ore deposits are mineral deposits of high enough grade that it's economically or legally recoverable with existing technologies. So what determines if a deposit is an ore deposit? So you need a high grade, so you need a high concentration of the metal or mineral that you're after. The type of ore, so some ores have higher grades or higher concentrations than others. Some ores have economically viable minerals that are bonded to other types of minerals than others. And sometimes the process of extracting and refining this can be more or less difficult based on the type of other minerals you find in there. So that's the type of ore you're after. The size and the depth of the deposit. So is it a big enough deposit that you want to build roads and infrastructure to get there and extract it? And the location, is that ore deposit in a country that's currently experiencing a civil war or has an unfriendly government to the government of the extraction company that's trying to go after those deposits. And the economics of ore deposits are that deposits were previously unprofitable to exploit that might suddenly become profitable. So what factors might contribute to that change in status? So supply and demand. Obviously, once the iPhone, for example, or laptops, or even just basic computing was invented, all of a sudden silica became very valuable. So countries that were sitting on tons of really good silica deposits that weren't selling that silica for much more than building materials or jewelry, all of a sudden that silica becomes very high in demand. Political changes, so the beginning of a civil war, the end of a civil war, that will affect whether or not certain ores are economically viable. This is sort of tied into what I was saying about supply and demand. If you have changing technologies, obviously that calls for different mineral resources. And so one really great example right now is electric vehicles. Electric vehicles need lithium-ion batteries. Those lithium-ion batteries need nickel. And so nickel is suddenly way more valuable than it's ever been. And right now, I think, especially during the pandemic, we were in a nickel shortage. So a country that was sitting on a bunch of nickel 200 years ago is suddenly much richer now because now they're able to extract and sell that nickel based on the technology that demands it. And there's environmental issues. A great example is, now these aren't minerals, but these are economically viable geologic products, coal and oil. Those were really, really valuable and continue to be valuable, but they are being extracted at lower rates in certain countries now and being bought by certain countries in lower quantities now because the environmental impact of extracting and burning fossil fuels is pretty dire, right? Due to its effect on climate change. And so environmental issues can change whether or not certain economic resources are viable and worth extracting. This picture here is a pit mine, the largest pit mine in the world, as far as I know. This is in Russia. And you can imagine the people in this little mining town here are going to run out of space. This is a very basic thing. They can't necessarily continue to mine around here because it's encroaching on their living space and things like that. So eventually, some of these mines just butt up against human development or environmentally protected areas in many cases. And so they can just no longer mine there. And so that will, in some cases, increase the price of those minerals because mines are shutting down. And so minerals are more scarce. So changing from an ore deposit to a mineral reserve. So in summary, you have changing demand, you have changing technology and lower costs. You have the discovery of new deposits or the exhausting of existing deposits. You have political conditions, and then you have aesthetic and environmental factors. And what this ties into is what we call national defense stockpiles. So a lot of times we have economic minerals that are in the ground and we know they're there, but we're not mining them yet because we're holding on to them. And we call that a stockpile. We do that with oil and gas. We do that with coal. We do that with nickel. We do that with iron. We do that with copper. We do that with silver. We do that with all sorts of things. So let's talk about the formation of mineral resources. So remember I talked about halite and gypsum. Those are evaporite minerals. And that's from shallow seas that had this stuff, these different magnesium chloride and calcium chloride minerals dissolved in them. And as those seas evaporated, it left behind the residue of those dissolved minerals. And then we also have gravity is another thing that will deposit minerals. So under specific chemical conditions, whether in a magma chamber or at the bottom of a seafloor, certain minerals will precipitate out of the liquid in the magma chamber. Remember, the first thing to precipitate out is olivine. So olivine will precipitate out and sink to the bottom. And so that olivine will form a deposit of olivine here. Remember, olivine is iron rich and magnesium rich. So if we're mining for iron or magnesium, we're going to drill into an exposed, cooled magma body, which we call a pluton. And that pluton is going to have a layer that started to cool first and settle to the bottom that has lots of iron-rich minerals in it. So we would drill there and extract those iron-rich minerals from that. And then if we were interested in other minerals, we would go up subsequently based on Bowen's reaction series and how each mineral cools and forms these kind of stripes. And at the bottom of the seafloor, the same thing is true. These banded iron formations have a lot to do with how much oxygen was available in the atmosphere and whether that stuff was exposed to the atmosphere. And so you'll get iron oxidizing and falling to the bottom, and then silica oxidizing and falling to the bottom, and it forms these alternating layers of iron in the form of hematite and jasper, which is a silicate. And so you can get ore bodies this way. And there are huge mines in Minnesota, in the UP, and in northern Wisconsin that sort of fueled the industrial age, and a lot of that came from these banded iron formations. Another thing that deposits ores is hot water, like I talked about. You can get that at these black smokers at the bottom of the ocean at divergent plate boundaries. And you can also get those from hydrothermal fluids moving through the crust near magma bodies. So the magma body heats up different ores and or heats up different groundwater rather, and that will dissolve things within the crust and deposit them. That's happening at the surface and at the bottom of the ocean in these black smokers. Here's an example of what would happen at the crust closer to the surface in the continent. Again, like I said, you've got hot water near a magma body moving away from the magma body. So at close to the magma body, it's dissolving all kinds of silica and metal that is just kind of sitting there latent in the crust. And then as it moves closer to the surface or further away from the magma body, it starts to cool down. And as it cools down, that stuff becomes solid again. Similar to how they make rock candy. If you've ever watched anybody make rock candy, it's very similar. You supersaturate the hot water. Because it's hot, it can hold stuff. And then as it cools down, that stuff precipitates out as a solid. And so you'll get quartz deposits in these veins. And a lot of times that quartz can be associated with other metals like copper and gold and silver. And so you get what we call a copper vein or an ore body vein. So let's talk about the consumption of minerals. So this is a figure that kind of blows my mind. This is how much every American consumes during their lifetime. So I'll give you a second to just kind of sit there and look at this. Bauxite, by the way, is how we get aluminum. There's gold, zinc, 80,000 gallons of petroleum, 50,000 pounds of various minerals, 32,000, almost 33,000 pounds of iron ore, almost 1,000 pounds of lead, 30,000 pounds of salt. This is, you know, if you live to be 80, 90, 100 years old, this is how much you consume in your lifetime. So economic mineral resources aren't going anywhere, obviously, as long as people keep having babies and keep driving cars and using technology and whatnot. Mining is going to be sticking around. And this is kind of a fun thing. So economic gold has 2.5 grams per tons of rock. So if you get a piece of ore that you want to mine gold out of, on average, it's 2.5 per ton of pure gold that you get out of that ore. To put that into perspective, an average wedding band has 5 grams of gold, so 2 tons of rock was mined to extract the 5 grams of gold that you use in your wedding band. How many tons do we have to mine? So a lifetime supply per US citizen is about 45 grams of gold. That's gold in the jewelry you wear, that's gold in the electronics you use, and that is 45 grams. So how many tons of rock is that? Well, 45 grams divided by 2.5 grams per ton. That's 18 tons of rock per person. So that's, what is it? 36,000 pounds of rock just to get the gold you use in your lifetime. So it's kind of crazy. How about iron? Well, the density of iron in ore is about 4 grams per cubic centimeter. Each U.S. citizen consumes 33,000 pounds of iron in their lifetime. So how much space does that take up? About 4 cubic meters, or 132 cubic feet. And here's an image over here on the bottom right. That's how much pure iron you use in all of the different materials that you consume that have iron in them, mostly probably vehicles and things of that sort, but also electronics, home building materials, and the like. Here's a chart of raw material, non-fuel materials, so mostly just minerals and metals consumption. And so at the beginning of the 1900s, we see this kind of steady growth through the Industrial Revolution. Then you have World War I, so there's a spike there. Then you have an increase during the Roaring 20s, when there was a lot of building. Most of the kind of older sort of foundational skyscrapers you see when you go to Chicago. You see a lot of these similar types of buildings, similar to the the Civic building we have here in GR down by the river there. A lot of that stuff was built in the 1920s. So there was a big building boom in the 1920s, the Roaring 20s. Then the Great Depression, that consumption drops off. Then in World War II, we see another spike as we were building up. And then a drop off. And then as the automotive industry began to boom, we see more consumption of metals and primary metals, and then we see oil crises and recessions and stuff, and obviously, so you can see that the general trend is building. But I also want to point out the recycled metals and industrial metals and whatnot are all kind of down here as well, right? And we see a steady increase there. Not to confuse you, one thing here is this major thing here is all construction materials, and those are related to minerals, but they're not metals per se. Let's take kaolinite. We use that to make plaster. Feldspar is used to make lots of different building materials. And so a lot of the minerals that you have in your kits are chosen for that reason. They go into building all sorts of things. So in your textbook, you'll see some of that in the little mineral and gem booklets that I put out. A lot of times you'll see what a lot of these minerals are used for. So I encourage you to research that as well. So for environmental impacts of minerals, to close out here, mining minerals affects the air, the land, water, and biodiversity. So for air, we have just the mining process itself, machines that extract, burn fossil fuels, and that puts particulates into the air, as well as the milling process will put particulates into the air. We have the footprint on land. So geographically, that giant hole in Russia, obviously that has a huge effect on the land. We have subsidence, which is when you're removing a bunch of material from the inside of a mountain, let's say. Eventually, the top of that mountain will collapse down into that space, and that forms a sort of sinkhole, and we call that subsidence. You have threats to habitat, and that could be either just removing the habitat, burning all the vegetation away in preparation of a mine, or drainage and water contamination. And that's pictured here, where if we think of this as a copper mine, let's say, and I'm making that up. I don't know if this is a copper mine, but I suspect it might be because of the color of this leach water here. We have what happen. We have what. Sorry, what happens is you get when mining copper, the natural byproduct of mining copper sulfide ore is sulfur, and so with that sulfur, that can sometimes be left behind if they don't clean up well, or the refining process isn't 100% efficient. There'll be a bunch of sulfur left over. That sulfur dissolves into the surface water here, and that can get in the groundwater, it can get in streams, it can get in lakes, rivers, um, and the ocean, and end up in your drinking fountain or water faucet. Um, so a lot of pollution from water, and that was a big deal in the Eagle Mine up in, which is a copper mine and iron mine up in the UP. A lot of the locals were complaining about high levels of sulfur in the groundwater, and so now mining companies are under much stricter scrutiny. I'll talk more about that when we get to mineral and energy resources. But this concludes the minerals lecture. It's a long one, 89 slides by my count. So thanks for hanging in there. Make sure to look back at the mineral groups and the highlighted minerals there, because that covers most, if not every mineral that you have in your kit. And so hopefully on Tuesday, you can start to put faces with names, so to speak, and I'll make sure you have the right minerals written down on your chart in the right places, and that you have the right properties on there, in addition to the properties that you observed on Thursday. So with that, I'll get started on igneous rocks and volcanism, and I will see you all on Tuesday. Have a great weekend.